Assalamualaikum and welcome back. We are still on surface integral of a scalar field. Now let's proceed with example. For example, let's solve item B, where here we are asked to evaluate y squared z squared integral of a surface sigma, where sigma is part of the cone, z equals square of x squared plus y squared that lies between the planes z equals 1 and z equals 2. So here you can see that the surface is given as z as a function of x and y, which means that we need to project our surface sigma onto the xy plane. So when z is a function of x and y, we need to project our surface sigma onto the xy plane, and if you have z in your scalar function, replace it with g of xy, and ds is still magnitude of normal vector dA. Okay, let's solve example B. So here we have a cone, z equals x squared plus y squared, so that would be a cone that facing upwards, 45 degrees. And we're not taking the whole cone, we only take part of the surface, part of the cone that lies between z equals 1 and z equals 2. Okay, let's sketch the cone first. So we have a cone of 45 degrees. The angle is 45 degrees. So we have 45 degrees here. And here we have 45 degrees as well. And looking from above, it's a circle. And here we have a circle as well. But the surface sigma is only part of the cone that lies between the two planes, z equals 1 and z equals 2. So this part of the cone is not part of the surface. So only this surface is the surface sigma. So the one below z equals 1 is not part of the surface sigma. Okay, so what we do is we project this onto the xy plane, since the surface is given as z as a function of x and y. So project this onto the xy plane, we have a circle, and project this, we have a circle as well. So our region R would be a region between two circles. Okay, so this would be our region R, which is the projection of surface sigma onto the xy plane. Now let's get the radius of our two circles. When z equals 1, excuse me, when z equals 1, the cone would be x squared plus y squared, square of that equals 1. Simplify this, we get this is a circle of radius 1. So when z equals 1, the radius of the circle is 1. So that would be 1, 1, negative 1, negative 1. And when z equals 2, we have x squared plus y squared, square of that equals 2. Simplify the equation by taking square of both sides. You can see that this is an equation of a circle of radius 2. So we have 2 here, 2, and negative 2. So if we sketch this in 2D, we have two circles. One is of radius 1, like so, and another is of radius 2, like so. Okay, is that right? Oh well, more or less. So this is our region. Okay, one is radius 2 and the other is radius 1. Negative 2, negative 2. So this is our region R. Okay, from the formula, we also need to find this. Okay, we also need to find this. Okay, that would be the magnitude of the normal vector. So let's look at our surface again. So our surface is given as this, square root of, okay, let's call this g of xy. And we need to find partial g partial x and partial g partial y. So differentiate. I'm going to rewrite this as x squared plus y squared to the power of a half. Then it would be easier for us to differentiate. Okay, first let's find gx, partial g partial x. differentiate g with respect to x. So we have a half, x squared plus y squared, negative a half. Differentiate the inside function, so we have 2x. So this is equal to x over square root of x squared plus y squared. Okay, and then we also need partial g, partial y. So differentiate g with respect to y, we get a half, x squared plus y squared negative a half, and then multiply with the derivative of the inside function, which is 2y. Simplify this, we get y over square root of x squared plus y squared, and yeah, we have both terms here, partial g partial x and partial g partial y. Now we can get the magnitude of normal vector. So ds is equal to square root of partial g partial x squared partial g partial y squared plus 1 dA. Okay, so now partial g partial x squared, that would give us, so when you square that, you get x squared over x squared plus y squared. And when you square this, you get y squared over x squared plus y squared, and we have plus 1 square root of that dA. Okay, alright, so now let's simplify the expression inside the bracket, inside the square root, sorry. So we can write this using a common denominator, let's say x squared plus y squared. So the first term would be x squared, the second term would be y squared. Here we have 1, so that would be x squared plus y squared. And when you simplify this, we get 2x squared, okay, and we have 2y squared, and we can simplify, oops, forgot dA, and we can simplify this as 2x squared plus y squared over x squared plus y squared square root dA, and from here we get this is equal to square root of 2 dA. So that is our ds. Okay, so that is our ds. Alright, so now we're gonna simplify this, evaluate this. Okay, so I'm gonna use the next page. So here we want to evaluate, make it bigger, y squared z squared ds over surface sigma. So this is going to be equal to double integral over region R on the xy plane. So y squared is still y squared, but this z here must be replaced by our surface, which is this. Okay, so z is replaced by x squared plus y squared square root, but then we have square. Okay, and ds is equal to this is our ds, which is square root of 2 dA, and our region is here. This is our region R. Okay, so this is our region R, which is a region between two circles. So now, as you can see, we are back to double integral. Since our region is part of two circles, we're going to evaluate our double integral using polar. Okay, so we're going to use polar. So y here is going to be r sine theta, so square that, and x squared plus y squared square root, that is r squared. Okay, but then we square that, so that will be r to the power of r squared, and then square root, that would be r, so we have r squared. We have square root of 2, so I'm going to put square root of 2 here since it's a constant. And then we have dA. dA is r dr d theta because we're using polar. Okay, alright, let me erase that. Okay, so x squared plus y squared square root, that is r. Square that, then you get r squared. Sorry. Okay, alright, now let's get the limits for r and theta. So back to our region here. Draw a straight line from the origin across your region. Okay, you can see that it doesn't start at the origin, but it starts on the circle of radius 1, and it stops on the circle of radius 2. So r is from 1 to 2, and for theta, it's going to be a whole circle there. So theta is going to be from 0 to 2 pi. Okay. All right, now evaluate this. I'm going to write it here. Okay, now let's integrate with respect to r first. So here, how many r do we have? So we have 2, 4, 5. Integrate with respect to r, we get 6. And we still have sine square theta. Replace r with upper and lower limits, which are 1 and 2. Okay. Replace r with 2. We have 2 to the power of 6 divided by 6 minus 1 over 6. That will give us 21 over 2. So we have 21 over 2, and we have square root again. Then we have sine square theta from 0 to 2 pi. Okay, to integrate sine square theta, we're gonna we're gonna use trigonometric identity by replacing sine square theta with 1 minus cos 2 theta over 2, and then integrate with respect to theta from 0 to 2. Okay, I'm gonna put 1 over 2 before the integration, so that would be 1 over 4. Integrate 1, we get theta. Integrate cos 2 theta, we get sine 2 theta over 2. And then replace theta with upper and lower limits. So here we have 21 square root of 2 over 4. We have 2 pi. Sine 4 pi is 0. That is upper limit minus lower limit 0. Sine 0 is 0. So we have 21 over square root of 2 pi over 2. Okay, and that is surface integral of a scalar field. Thank you.